Okay, okay. Thank you very much.
I started it. Okay.
Okay, okay. This is basically because, of course, being a European Horizon 2020 project, we need to report also, we need to have a track record of our activities. Yeah. So I have a small presentation about the project to initiate the team. And then, of course, there is a very interesting lineup for today's workshop, which is you know, I know most of them actually. So it is very nice to see Chiara here from Imperial College, um, and others colleagues from Manchester. So yeah, I'll share my screen. Give me a second. Can I share my screen? Yes. Um, Give me a second. Share screen. Okay. Yeah, being okay. Now you can see my screen, I guess, right? Yes. And you can hear me, right? Yes. Okay. Um, the JUMP2Excel stands for the Joint Universal Activities for Mediterranean PV Integration Excellence, and it's a twinning Horizon 2020 project. And I understand that there is a number of international participants. Uh, and if you are wondering where is Malta, so this map should help you. Malta is actually in the middle of Mediterranean. We receive the most solar irradiance um, throughout the within the Mediterranean as a state. Yeah. Um, and the idea is that photovoltaics is solar energy is the priority, let's say, renewable energy resource in Malta. The themes of the projects are very wide and varied. Today we are looking more into the integration solutions and system level, but also we had recently a school which was based on emerging photovoltaics devices and techniques. Yeah. Um, and how can you participate if you are interested? So we have different actions within the project. These includes workshops like this one. They actually changed to online, but eventually we will also visit Manchester and our advanced partners. We have schools. We have one remaining school I will talk about later. Okay, internships, mentoring, etc. Yeah. So please feel free to stay in touch within the webpage and the social medias portals of the project. And we have also a stakeholder participation where you can also participate. A little bit about MCAS Energy Research Group. We developed this group very recently in 2014, and we attracted substantial amount of external funded, being actually, one of the most developing, well, the only developing really energy related and power systems related research group in Malta that have developed so significantly in terms of funding externally. Um, we have a couple of other projects, um, and I will talk also about our members. And we've been collaborating with the University of Manchester for a while now as well. So the partners, probably Jovica can introduce also a little bit more about Manchester later on, yeah, and also our colleagues. So the partners includes the University of Manchester in UK as an academic partner, okay. We have CENER, the National Renewable Energy Center in Spain, and CEA, which is the largest research and dissemination organization in France. Um, how you can engage. These are the links where you can engage with us and follow us. I encourage you as well to, while this workshop is ongoing, there will be posts. Please do like, share, whatever. Yeah, we would like to make an impact as much as possible. Um, in March 2022, we will have the Jump2Excel, the last Jump2Excel school. And for this, actually, we invite interested participants. We have even travel and participation support. Hopefully, we can do it in person. And we are looking forward for that. So please visit our webpage and register. We are mainly five full-time people within the MCAST Energy Research Group, plus some master students. So here are the people involved. We have Renata, Vibhu, Somesh, and Marcin. And in parallel with the Jump2Excel, we also have another twinning project, which is called NEMO, which is related with electric mobility. So these are also two events. One is the second edition school, the coming November. Similarly, participation is supported there. This is being very sensitive, my mouse, for some reason. Okay. And there is also a workshop similar to this in July. This is the school 3 of Jump2Excel, which I was referring to. The registrations are already on. And if you like to have travel support, introduce a little bit your research to us, you can come and we can support the travel and participation. There is also the MatPower 2022 in Malta, so keep this in your calendar. You can see probably a beautiful view of Malta in my background some time ago. So that's to encourage you more, yeah. Otherwise, I look forward for this workshop, and thank you for all the speakers that has committed themselves to share their knowledge with us. We look forward for a very positive discussion, yeah, and yeah, and thank you for all the participants that showed interest and they are with us. Yeah, thank you.
Thank you very much, Bran. Very timely and well-managed presentation. Before we start with the first talk, I'll just like once again to thank my colleagues from the University of Manchester and from the Imperial College London who decided or who had agreed to talk to you today. We at both institutions, but I can talk more about Manchester, I suppose, have been doing a lot of work in the area of PV materials and general integration of renewables, in particular PV in power systems. And this will be I wouldn't say a cross-section, but a sample of the research done at these two institutions in the United Kingdom. And I deliberately opted to combine two institutions rather than use only Manchester view on the problem, because no one has a monopole on research in an area. So because it's organized by Manchester doesn't necessarily mean that all the presenters should have been from Manchester. That's why I have participation from colleagues from Imperial College London, that I'm also involved in some other project. So there are, on the website where you were asked to register for the workshop, there are abstracts and biographies of all the presenters, and I will not spend any time on introducing them by reading their biographies from the web. You can do that yourself. We will start with the first talk by Dr. Robert Hoy from Imperial College London in a few minutes. And then we will follow with Professor Martin Hassel from Manchester. Then we'll have a lunch break between 12 and 1 UK time, or 1-2 Central European time. And then we'll continue with presentations from, again, Manchester, Alessandra Parisio, then Imperial College, Chiara Candelise, and then at 3 o'clock UK time, or 4 o'clock Central European time, the final presentation by Dr. Berkeley Solomon from the University of Manchester as well. So it will be 5 hours of talks for you. I am aware that maybe not all of you will be joining all the talks, Some may join one, some the other, some may stay for all five. That will depend on your personal preference. At the moment, as I can see, there are 36 of us on the call. We'll see how the things develop as we progress. Each participant will, each presenter will talk for some minutes, and they will have time for questions and discussions. I think there is plenty of time provided for all of your questions. The easiest way to handle these questions would probably be that at the time when you want to ask the question, you unmute yourself and ask the question. If you can do that, it would be excellent. Otherwise, you can use the chat, but the chat may be delayed because we will have to monitor who came first and go through chat, because there are a very large number of people registered. It may be a lot of questions in the chat that I will not be able to manage all of them. I will have Dr. Anmar Arif here from Manchester also, who will be monitoring the chat room, if you like it, as well. So in case you ask your question in chat, we'll try not to miss anything. But in case we do, please unmute yourself and ask your question directly. I'll try to coordinate many people talking at the same time. But this is just to make sure that all of your questions and comments get addressed without missing anyone, because as you know, by now probably a year or more working on this on different online platforms, sometimes it's confusing who is talking and who is writing questions in a chat room. So it can be pretty tricky to follow all of these at the same time. So without further ado, I invite Dr. Robert Hoy to talk to us as the first speaker. His topic is photovoltaic materials systems for the energy transition. And as I said, Robert Hoy is from the Imperial College London. He is a Royal Academy of Engineering Fellow. So he has been working in this area for quite a while and produced some fantastic results. So I'm sure you will enjoy his talk. So Robert, the floor is yours. I can see you already shared the screen. Thank you very much. So Robert.
Well, thank you, Jolika, for the very kind introduction, and also thank you for the opportunity for me to present my group's work and some of the ideas that we've been looking into with you all today at this workshop. So as mentioned, my name is Robert, and I'm a lecturer and a Royal Academy of Engineering Research Fellow at in the Department of Materials at Imperial. And my topic today will be about photovoltaic materials for the energy transition. So before we get started, I just wish to very quickly introduce to you my group. So I started at Imperial last year in January, and right now I have a postdoc and 3 PhD students at Imperial, and we'll have another student joining us later this year in October. Before this, I was a research fellow at Cambridge. I've still got 5 PhD students working with me there. And 2 of my former students have now graduated, and they're now working in both the UK and also in the Netherlands now. So we're a very international team. So at Imperial, our lab is based at in the Imperial spoke of the Henry Royce Institute. And I can see that a lot of people here are from Manchester, so probably all about the Royce. So the Imperial Royce is based in the new Michael Uren building, which is at Imperial's White City campus, which is a new high-tech campus that Imperial has. And we're on the 8th floor of this building. So that whole floor is the main embodiment of the Imperial Royce and has a range of physical and chemical vapor deposition facilities, as well as a clean room and some new characterization equipment. And once the Imperial spoke of the Royce is officially opened later this year, this will be open for anyone in the UK to access by the standard schemes available through the Royce. And our lab is embedded on this floor here. So the theme of the Imperial Royce is atoms to devices, and this involves partners from Leeds, Manchester, as well as Cambridge. And last year, one of the activities we were collectively involved in was a series of roadmaps commissioned by BEIS, which is part of the UK government, a series of roadmaps to identify what is needed in order for us to reach our legislated ambitions to achieve net zero by 2050. So this roadmap was comprised of a series of different technologies, and one of those was on photovoltaics, which is the one that I was involved in. So here you can see some figures from a report made by the UK Committee on Climate Change, published in 2019. And this was published before the UK government adopted legislation to reach net zero by 2050. And back in those days, the ambition was an 80% reduction in greenhouse gas emissions compared to 1990 levels. And you can see from this figure here that even achieving this lesser ambition requires us to almost completely decarbonize the power generation sector, as well as substantially reduce emissions from surface transport and buildings in particular. And in this report, they outlined a further ambition scenario, which specifies that to go beyond 80% reduction, go towards 96% reduction in CO2 equivalent emissions. And this requires low carbon generation to increase by over a factor of 4. So of course, going beyond this and reaching net zero by 2050 requires a further increase in this low carbon generation. And that of course requires a substantial acceleration in the deployment of renewable generation technologies. And one of those of course is photovoltaics, which harvests sunlight to produce cleaner electricity without emitting any greenhouse gases. But although PVs is a fast growing area in the UK and many parts in the world, right now photovoltaics only contributes quite a small fraction to the total electrical energy that's generated in the grid. So there needs to be a significant acceleration in deployment if we are to allow photovoltaics to make a substantial contribution in our path to net zero. And that can be generalized worldwide as well. If this box here represents all the energy that the surface of the Earth receives from the sun, this would represent the actual electrical energy that's needed worldwide right now. And you can see there's a 3 orders of magnitude difference, but despite the significant potential of solar energy, only 1% of all electricity generated worldwide is from photovoltaics. And in the UK itself, the potential for photovoltaics is 100 times larger than the use that we are putting it to right now. So there's a lot of potential for further usage of this source of energy. And in the photovoltaics roadmap last year, we had a discussion about what's needed in the future for the UK to meet this challenge of accelerating the deployment of this technology. So this roadmap was led by the Henry Royce Institute, and they commissioned the Institute for Manufacturing in Cambridge, which is a consultancy service which administered the roadmaps. And the actual content itself was a collaboration through a series of discussions from academics from 14 institutions, as well as companies across the UK working in the sector here. And this figure here illustrates to you the scope of the photovoltaics roadmap. It was actually a collection of a series of roadmaps on 3 different materials, as well as a series of different technologies, such as multi-junction devices, building integrated PV, as well as photovoltaics for automotive and space applications, and also PV for applications which don't move. And this was mostly indoor PV. And there was also a roadmap involving predominantly industry to discuss some of the challenges in bringing new technologies to market. So you can see here that the 3 main materials which were, which had their own roadmaps were silicon, carbon telluride, and these perovskites. And the reason for that can be seen here. So this is a plot from the Fraunhofer Institute for Solar Energy in Germany. And this is taken from their photovoltaics report from last year. And you can see that 94.5% of all the photovoltaic materials produced worldwide is based off crystalline silicon. And this is by far the dominant technology in the PV market right now. And it's definitely going to make, it's definitely going to feature in our efforts to reach net zero by 2050. And the rest is comprised of thin films, which right now is mostly based off cadmium telluride. So these are the two dominant materials which have the greatest scale of production. Over here, you can see a comparison of different market sizes for different applications. And of course, the biggest market is for residential and utility scale PV. So these are photovoltaics that you see on the rooftop or which you see in solar farms. And this is by far the biggest sector, which is exponentially growing. And the composition of the materials which are used for devices used for in this sector here are mainly reflected by what you see in this plot here. So mainly silicon and a little bit cadmium telluride. But there's also other markets as well, which are also growing rapidly. For example, there's photovoltaics used for building claddings, as well as indoor PV. And you can see that the slope on this log linear plot for indoor PV is a lot higher than for these other sectors here. So although indoor PV is relatively small right now, is a fast growing area and has an annual compound growth rate of 70%, which is a lot higher than for residential PV. And for these two other areas, two smaller markets, you can still use silicon and cadmium telluride, but there are actually a lot of advantages to using emerging technologies. And this is where the new materials that academic groups such as my own group are developing can play quite a significant role. So of course, in 30 minutes, it's not possible for me to talk in detail through every single roadmap that was in the overall photovoltaics roadmap from last year. I'm just going to give you some of the highlights through the three main materials for residential PV right now, as well as two of the important technologies. And here I'm just going to keep the discussion high level and talk about what the status is for each of these technologies and what are the future materials and device challenges that would need to be overcome to improve their suitability for commercial applications. And this is going to finish with a perspective which collects some of the main points from all the different PV roadmaps, some of the opinions about what's needed in terms of investment in the UK to bring new technology to market faster. Okay, so let's get started with the first section on silicon photovoltaics. So silicon, crystalline silicon has a crystal structure that you see here. It has the same crystal structure as diamond. So you have a tetrahedral arrangement of silicon atoms which form covalent bonds. So if you break these bonds, for example, by having vacant sites, or even just at surfaces, then you have dangling bonds which interfere to create defect states in the middle of a band gap. And that causes irreversible losses in energy through a process called Shockley-Reed-Hall recombination. So a lot of the history of development of silicon photovoltaics was about addressing these defects, how we can process the materials to minimize the densities of these defects, as well as how to passivate the dangling bonds at the surfaces. And on the bottom here, you can see three common device structures for silicon photovoltaics. And right now, the most commonly used one is this PERC structure. And PERC stands for passivated emitter and rare cell. So the name tells you what it's all about. It's about passivating both the front and the back contacts. So you can passivate these dangling bonds and minimize surface recombination. So the front surface, this is called the emitter, where you have a homojunction between P and N-type silicon. You can see that the entire surface is covered with this blue passivation and anti-reflection coating, apart from the small areas where you have metal contacts. And the rare is also passivated. For example, what's commonly used is alumina, which is grown by plasma enhanced CVD or by ALD. And you only have small holes milled, etched into that, where you have the local contact for extracting holes from the p-type silicon layer. So currently the state-of-the-art efficiencies from these PERC devices is 23.4%, but in the future, this is predicted to saturate to 24.5%. And there are these other device structures which aren't as common in industry right now, but which can give us higher efficiencies. So there's the silicon heterojunction cell. And this device, both the front and back surfaces are passivated by having amorphous silicon. You can see there's intrinsic amorphous silicon as well as NMP-type doped amorphous silicon for charge extraction in this device. And this passivation method is very successful. It's led to the highest open circuit voltages among silicon devices. But the disadvantage of this device structure is that the amorphous silicon absorbs light, so it gives rise to parasitic optical losses, which limits the short circuit current densities. And a structure that was developed to overcome this limitation is called the interdigitated back contact solar cell, where you have both the P and N-type contacts, both at the back surface. They're interdigitated like having fingers, and they extract both the electron holes just at the back surface. And so here, you shine a light in from the front surface, and in principle, you can have passivation layers that don't have such a large parasitic optical absorption. At the very least, you don't have these metal fingers anymore on the front surface, which can cause shading losses. But in reality, what people have found is that the most efficient IBC cells actually do use this heterojunction passivation. They do use the amorphous silicon to passivate the front and back surfaces. And that has led to the record efficiency for crystalline silicon under non-concentrated sunlight, which is 26.7%. And that's very close to the practical efficiency limit for this device structure of 27.1%. The disadvantage of this structure is that it's more expensive because it's more complex to have these this interdigitated back contact structure. So of course, to justify the higher cost, these devices need to have high efficiencies. And over here, I have a comparison of the efficiencies of these different technologies compared to the theoretical limit, the radiative limit for different band gaps. You can see that these best efficiencies are scattered about the 75% line, the 75% of the radiative limit line. I should mention that even though for a material with a band gap 1.12 eV, which is silicon, even though the theoretical limit is above 30%, in reality, the maximum efficiency that you can achieve with this particular material is lower than that and is limited by Auger recombination. So actually the highest efficiency you can get is about 29%. So you can see that after 6 decades of development, silicon technology has approached its efficiency limit now. So what are the challenges moving forward with this technology? So for the PERC cell, what's needed is to improve the minority carrier lifetime and to reduce resistivities, and that's to improve the fill factors further, so you can have high efficiencies. And there's another important factor called bifaciality, because if you think about a solar cell in a solar farm, for example, the solar cell is tilted. So you normally absorb light from the front surface, but you also get light reflected from the ground. And also at different times of the day, the sun could be on the horizon. You could be getting light primarily coming from the back surface rather than the front surface. So bifacial devices are able to absorb and harvest light from both front and back surfaces. Because of the way the PERC cell is made right now, the bifaciality, the ability is relatively low, only 65 to 75%. So modifying this device structure to improve the ability to absorb light from the back surface as well will be able to boost the efficiencies further. And this also needs to further reduce the contact resistance at these local contacts, as well as develop better passivation methods. For the heterojunction cell, as I mentioned, it's limited by parasitic absorption from the front layer. And usually there's also transparent conducting oxide deposited on top to reduce the series resistance. So these are limitations that need to be addressed. And another limitation is the fact that you have amorphous silicon. So if you heat amorphous silicon up to above 200 degrees Celsius, you would then crystallize that, and then you change the device structure. So that's another limitation, which, for example, prevents using industry standard metallization methods. And one of the main reasons why this device structure isn't so commonly used in industry right now is because right now it's more expensive to produce compared to the PERC cell. Cost is also an important factor with the interdigitate back contact cell. So developing methods to reduce the processing complexity will be important, as well as improving service passivation and reducing optical losses. And across all these different technologies, as well as other different device structures that companies are developing right now, some of the common challenges are to extend the lifetime of these devices. I mean, silicon is a very mature technology, and the degradation rate is very low right now compared to some emerging materials. And people understand the degradation processes quite well. So there's methods to do accelerated degradation testing and for manufacturers to certify devices to 25 to 30 years. But people have ambitions to extend this to 40 years. And this lifetime has an influence in the overall levelized cost of energy. So efficiency is one factor that feeds into that, but lifetime is also another important factor. So increasing this will push down the LCOE so that silicon photovoltaics are more cost competitive compared to fossil fuel sources, which will encourage more investment and more uptake. And I think the next speaker will be talking about degradation issues, so I won't go into detail into that. And also another common challenge is to lower the cost of production, for example, by having thinner wafers so that in each ball of single crystal silicon that you can have more devices that you can cut from that, as well as having reduced materials loss when you're slicing wafers from a ball of silicon. And also to reduce the processing temperature in order to decrease the carbon footprint for manufacturing silicon photovoltaics. So that was a summary of the silicon PV roadmap. So I'll now go into the second material, which is cadmium telluride. And you can see that this technology has a very different device structure. And the reason for that is because this is what we call a thin film technology. If you're making silicon, you would start with a wafer of silicon and then process different layers onto that. Whereas for cadmium telluride, you will actually start with a glass substrate that's coated with a transparent conducting oxide. And then onto that, you would deposit the buffer layer, as well as the absorber layer and the back contact. And what is being done to get the best efficiencies now is to alloy selenium into cadmium telluride, which lowers the band gap and improves its spectral match with the solar spectrum. So, the best efficiency reported for cadmium telluride is about 22%, which is very close to the 75% of the radial limit line. And the highest module efficiency is very close to that. It's reported to be 19%, and that's reported by First Solar. So right now, the scale production of cadmium telluride isn't as high as for silicon. In fact, it's about an order of magnitude less than, in fact, more than an order of magnitude lower than that for silicon. But still, compared to other emerging technologies, the scale production is relatively high. It's 6 gigawatts per annum, and that's expected to expand to 8 gigawatts per annum, which may have already been reached. And the UK has a very strong stake in this technology. Although the UK doesn't itself manufacture cadmium telluride solar cells, one of the British companies, which is NSG and used to be called Pilkington, makes the transparent conducting oxide coated glass, which is used in cadmium telluride solar cells. And that's quite significant because this TCO coated glass accounts for 50% of the cost of the solar cell. So these are some of the challenges that people in the roadmap identified. One of the challenges is to increase the efficiencies to reach the 75% line. And you can see that corresponds to about 25% efficiency. which can be done by reducing losses in the open circuit voltage by improving carrier lifetimes. There's also important to improve the device stability and pass faith surfaces better, as well as to make devices that can operate in a bifacial manner. And it's also important that there's greater uptake of this technology in industry, because we all know about the effects of the economy of scale on the cost of technology. So right now there's only a small handful of companies actually manufacturing cadmium telluride, but the potential is a lot greater than that. If we look at tellurium, the supply of tellurium is relatively limited, but still there's enough tellurium in the world to make enough cadmium telluride solar cells to reach 10 terawatts of deployment worldwide. And although tellurium and cadmium are both toxic elements, cadmium telluride itself is not toxic, and the devices are encapsulated. And the companies that have manufactured this so far have quite an effective recycling scheme, such that 95% of modules are recycled. Okay, so that covers the two mainstream technologies in the market right now. And now I want to talk about the main emerging technology that is just at the point of moving from lab to market. And these are the lead-Taylor perovskites, which have taken the academic world by storm, and which are a lot of people who used to work on different technologies like organic PV or dye-sensitized solar cells are now gravitating towards these lead-Taylor perovskites. So why is that, and what is this material? So when I talk about perovskites, I'm referring to a family of compounds with this crystal structure that you see here. And in these compounds, we have a B-site cation, in this case is lead, which is octahedrally coordinated with halides, for example, iodide or bromide or chloride. For solar cells, usually iodide. And these lead-Taylor octahedra share corners to form this symmetric, 3D symmetric unit cell. And usually the space group would be a cubic space group or a tetrahedral space group. And to keep the whole structure together, you have this large A-site cation, for example, methammonium or a mixture of cesium and formamidinium, which occupy these cube octahedral vacancies. The advantage of this material is that it can be made by solution processing, processed at very low temperatures of up to 100 degrees Celsius. Now contrast that to silicon, which needs to be processed at above 1400 degrees Celsius. And you can see that the carbon footprint of this technology will be quite low. And in fact, if you look at the energy payback time, for crystalline silicon, the energy payback time, which is the time in which you need to have a solar cell outdoors to harvest energy before it recovers the energy it took to make that technology. For crystalline silicon, the energy payback time is a few years, whereas for the perovskites, it's only a couple of months. Simply because this technology is now very efficient, but the energy required to process this material is quite low because it requires relatively low processing temperatures. So this slide summarizes, this slide summarizes the history of the development of this technology. It was first reported in the solar cell in 2009 by a Japanese group, and they were thinking about this material as an alternative to a dye in a dye-sensitized solar cell. And this was picked up by a group in Oxford who made devices with this structure here. So you can see there's still this mesoporous scaffold, which is from the dye-sensitized solar cell, but this time still using a liquid electrolyte that uses solid state whole transport material. And suddenly the efficiency shot up from about 4% to 11%. And this was back in 2012. And that's when a lot of people started paying attention to this technology. And there was a very fast development since then. And now, these days, the certified record efficiency is 25.5%. So that work hasn't yet been published. The highest published efficiency is 25.6%, with a certified value of 25.2%, which was the record efficiency from last year. And there were two papers published just at the beginning of this year, both in Nature, reporting these 25.2% certified perovskite devices. And if you map that out onto this chart here, comparing with the relative limit, what you can see is that already even though the perovskites are much younger technology, already the perovskites have surpassed the best efficiencies of cadmium telluride. And they've gone past the 75% of the radial limit line, and they're at the cusp of matching the best efficiency for crystalline silicon devices. And that is really quite remarkable for a solution-based technology made using normal lab-based equipment rather than an industrial production facility. And some of the recent advances which have led to these best efficiencies have included passivating the top surface, as well as passivating bulk defects within the perovskites, and which is exactly what has been done with silicon to get the best efficiencies. So earlier this year, I and some other colleagues wrote a future energy piece for JUL to discuss some of the current challenges which need to be overcome to move this technology from lab to market, because there are already several companies which are just at the cusp of commercializing this technology. And some of them even hope to bring the first products to market as early as the beginning of next year. So one of the challenges is to further improve performance, because this record efficiency is very good, but it's still the practical efficiency limit is 30%. So there's still a lot of room to go in terms of efficiencies. And what's really enabling that is the fact that the fundamental understanding of this technology is beginning to catch up with the efficiencies. And that includes being able to look at this material at the atomic level. So what you're seeing here is a high resolution transmission electron microscopy image of this material of formaldehyde lead iodide perovskites. And this used to be quite challenging, because it used to be that if you put the perovskites under a high energy electron beam, it used to just burn the material. And the way these people got around that problem was by having low dosage rates, a low dose rate for the electron beam. And so here you can see, for example, there's amorphization at this triple boundary junction, as well as a line of vacancies extending along this grain boundary here. And that explains why what people have observed before, when people have done spatially resolved photoluminescence measurements, where people have seen that the grain boundaries are darker than the bulk of the grain, because the grain boundaries accumulate point defects. Another thing that needs to be done is to further develop better strategies to passivate surfaces and interfaces. There's already been a lot of work on using long chain ligands to passivate the top surface, but there also needs to be work done to passivate the bottom surface, which is more challenging because this is a solution-based technology. So you can wash away the passivation layer. And an emerging concept is to use self-assembled monolayers, which could anchor themselves to the substrate. Apart from efficiency, what's also important is scale of production and speed at scale. Right now, the best efficiencies are made using photovoltaics with an area smaller than a fingernail. But if you want to make an impact on reaching net zero by 2050 across the world, you will have to manufacture several million meters squared of this technology. And so scale is important, but speed is also important, because the more devices you can make per manufacturing hour, the greater the profit, and therefore the easier it is for manufacturers to scale up production. So this compares the processing speed for various large area deposition technologies. And you can see that one of the fastest technologies is this rapid spray plasma processing technique. And there's also blade coating, which is what you see here. And the third important factor is, of course, stability. And that is really encapsulated by this, this figure here, which calculates the levelized cost of energy versus the lifetime. And you can see that beyond a, beyond a 5-year module lifetime, changing the efficiencies doesn't really make a huge difference anymore to the levelized cost of energy. It's really the module lifetime that has a bigger effect. So developing a better understanding of what are the main degradation pathways in perovskite solar cells, and developing protocols to do accelerated testing of the stability will be important in the future. Okay, so now I want to talk about some more advanced technologies for photovoltaics. And the first of these two is the multi-junction devices, which is where you take multiple solar cells together and get them to work together. The reason for that is summarized in this line. So if we look at silicon, because I mean, silicon is the most common solar cell you would buy on the market right now. And in the United States, you will pay $2.80 per watt for a silicon solar cell. Of that $2.80, only 35 cents is actually going into the production of the module itself. The rest is dominated by profit, by overheads, by the balance of systems, by installation labor. All these other things dominate the cost of a silicon solar cell. So if you improve the efficiency of silicon by 1 or 2%, you're not going to change this overall cost that much. What you could do is make a different structure, and maybe this adds a little bit to the cost. Maybe instead of paying 35 cents, you pay 40 cents. But if you can increase the absolute efficiency by an absolute value of 10%, then you increase the power produced, and therefore you can significantly decrease this cost per watt ratio. So efficiency is an important lever for the levelized cost of energy for photovoltaics. And the way in which you can get this substantial increase in efficiency is if you take different solar cells and get them to work together. The reason why you saw that there's a limit to the efficiency that you can get from a single junction device is because there's only one band gap. So you can only absorb light with energy above the band gap, but the energy in excess of the band gap is lost as heat. And if you can bring two solar cells together, then you reduce the energy loss of heat and convert a larger fraction of the solar spectrum into electrical energy. So these are called tandem photovoltaics. You can either make two different solar cells and electrically connect them, or you can monolithically integrate the two together. These are called the two-terminal tandems. So a tandem technology that's gaining a lot of interest and attention in the field right now is based on perovskites and silicon. Because as you saw earlier, the perovskites are very cheap to make. So if you make a perovskite top cell over silicon, you don't really increase the cost that much, but you can increase the efficiencies a lot. And already, the record efficiency for this technology is 29.5%. And that's significant because this is greater than the efficiency limit for single junction silicon devices. Remember, the efficiency limit for single junction silicon is 29%. And this is also right at the limit, practical limit for a perovskite single junction device. And people predict that in the future, it's realistic to make modules of perovskite silicon tandems that can reach 35% efficiency. So that is really quite exciting, which shows that you have a realistic device which can overcome the theoretical limits in efficiency for each of these individual subcells. And this paper here analyzed the effect on the levelized cost of energy. So if you compare perovskite silicon tandems versus a standard PERC cell, you can see that there's a reduction. But actually, it's not really a big reduction because you're still using the capital-intensive silicon bottom cell. And you can in principle make cheaper devices just by having a perovskite device by itself. There are arguments in the field about whether that's really feasible because silicon has the advantage of scale. So if you have a new technology and you leverage existing technology that already has a large deployment, then that may be a better way to have a new technology deployed at scale. So arguments about whether best to use perovskite by itself or perovskite silicon tandem. But just for the sake of LCOE by itself, you can reduce the LCOE below that of a single junction perovskite device if you replace the silicon bottom cell in the tandem with another perovskite, which has a lower band gap. And this perovskite tandem is another emerging technology which is undergoing rapid developments. And now I just want to talk about the final photovoltaic technology, which is indoor photovoltaics. And the reason why these are important is because one of the biggest new energy increase in energy will be from something called the Internet of Things. And this is something you may have heard about before. It describes an ecosystem of autonomous devices which can communicate together and therefore embed intelligence into infrastructure. So that leads to, for example, smart homes or smart cities. And this intelligence can lead to better usage of resources. So in itself, the Internet of Things can be a big contributor to reducing carbon emissions from our cities and from our buildings by using, for example, by having more efficient ways of heating the home, for example. And it's predicted that by very soon we'll have 75 billion of these Internet of Things devices. They'll mostly be small and autonomous, so you can't really just plug them all to the wall. So most people would use batteries to power these autonomous devices. As you all know, batteries have limited lifetime, and they need to be replaced or recharged. And it's feasible to do that right now, but if you have tens of billions of these devices, or if you have even 1 trillion of these Internet of Things devices, it's not really practical to replace that many batteries per day. Plus, if you're throwing away millions of batteries every single day, you're creating a substantial sustainability challenge if you think about the waste that will create. So we can overcome these challenges if we can use a photovoltaic device in each of these autonomous Internet of Things devices to harvest the freely available energy from its surroundings, whether it's from sunlight outdoors or whether it's from indoor lighting if it's used indoors. And this is the area in which crystalline silicon doesn't work so well, because crystalline silicon dominates the outdoor market because it's efficient and cheap. But indoors, the efficiency drops quite a lot because on a low level illumination, the dark current dominates compared to the light current, and that substantially reduces the efficiencies. Because of that, amorphous silicon has gained more traction in the industry, but even that isn't really that efficient. At best, it's 20% efficient indoors, but most devices are less than 10% efficient. So that's why people have looked at these emerging technologies, the dye-sensitized solar cells and organic photovoltaics, which can outcompete these silicon-based technologies in terms of efficiency. And the perovskites, people recently thought about taking perovskites indoors, and almost straight away, the efficiency skyrocketed to 37%, which is really quite remarkable, already outperforms the best dye-sensitized and organic PVs. And you can see that the band gap for this perovskite is well below the optimum value. So we can probably expect further improvements in efficiency in the near future from these indoor PV. But of course, the limitation of the perovskites is that they contain lead. And for outdoor deployment, lead is not a problem because lead is exempt from the European regulations. The restriction has the substances directive. But for indoor applications and for consumer electronics, that's not the case. So there's a question as to whether you can actually use lead-based solar cells, lead-based photovoltaics indoors. And that motivates the development of new technologies, new materials that don't have this toxicity issue, which are sustainable, but which can also be efficient. And this area only recently emerged over the past few months, where I and colleagues looked at some emerging bismuth and antimony-based absorbers. And people have been looking at these materials as non-toxic alternatives to the perovskites for outdoor PV applications. And the efficiencies haven't been anywhere near as close as the perovskites, partly because these materials have wide band gaps, close to 1.9 eV. But that band gap actually is the optimum value for indoor light harvesting. And I show for one of the materials, bismuth oxyiodide, that just by taking the device indoors, the efficiency shot up by a factor of 5, simply because of the better spectral match of the absorption profile versus the emission profile of indoor lighting. And we showed that these devices were already sufficient for powering inverters, which is one of the components you would use in IoT electronics. And we showed that the efficiency limit, so the optically limited efficiency for these materials can actually be a lot higher than for amorphous silicon, and also in some cases higher even than for the perovskites. So this is a new area of research that has a lot of promise. Okay, so now I just want to summarize some of the main perspectives that academia and industry put forward in the PV roadmaps from last year. So across all different technologies, some of the main challenges, well, the first challenge is still fundamental understanding of the different technologies. And that applies even to silicon. Even though silicon is a mature technology, there's still things we don't understand. For example, what causes light-induced degradation, for example. So new fundamental insights will be very important. as well as scaling up and prototyping new technologies. And right now in the UK, there's a gap between technology readiness levels from 1 to 3 and beyond that. It's also important to extend device lifetimes from where they are right now, which is about 25 years to 40 years by 2050. And this is important to reduce the levelized cost of energy. And it's also important to develop materials, especially electrodes, which make up quite a large fraction of the cost, based off non-expensive and non-scarce elements. So going silver-free and going indium-free. If we can do this, the opportunity will be to achieve low capital intensity solar cells with extended stability. So these can be lower cost and more promising for people to invest in. I didn't really talk about this, but you can also use them integrated into buildings and to architecture to make more sustainable buildings. In fact, you can even make carbon neutral buildings. With the new thin film technologies, you can make lightweight devices that can be integrated into electric vehicles to extend the range of electric vehicles. You use them in space, and you can use them indoors to power Internet of Things devices. And these technologies will be important enablers for other renewable technologies, such as for solar fuels to produce hydrogen, which is important for our hydrogen economy. And there was actually another roadmap from last year on hydrogen. The requirements for doing this. Well, first of all, there needs to be dedicated funding from government for PV absorber and contact material development, as well as national facilities for degradation testing and device metrology. And since when we launched roadmaps, there's been activity in this area here, where there's a recent collaboration between Imperial and the National Physical Laboratory to make a national facility for device metrology. And that's not just for PV, it's also for other technologies such as low loss electronics. And there needs to be investment in the UK for catapults and pilot facilities so that the new technologies being developed in the UK can stay in the UK and be manufactured here. And it's also important to bring together key stakeholders, not just people doing the R&D, but also end users such as architects who would use photovoltaics for building integration, as well as training networks to build up the pipeline of skills in the UK. So to summarize, photovoltaics are an important path for us to reach net zero by decarbonizing power generation, but also in many, at the utility scale, but also in many other unconventional markets, such as in buildings and indoor light harvesting. Although crystalline silicon currently dominates the utility scale market, it has limitations. And this is where emerging technologies can come in and play an important role in further improving efficiencies or being used for applications where silicon doesn't work so well. And among the many requirements, one of the most important, I think, is the cooperation between stakeholders in different sectors, as well as the investment in scale-up infrastructure and advanced metrology. So with that, I'd like to thank you for listening. And what I presented was a summary of the quite detailed roadmap on photovoltaics from last year. And if you're interested, I really encourage you to follow this link to read the roadmap in detail. And also there's this short paper here, Future Energy piece that I published earlier this year, which summarizes some of the important future challenges for the metal halo perovskite photovoltaics. So thank you very much for listening, and I'll be very keen to take any questions.
Thank you very much, Robert. Excellent talk and excellent timekeeping. So if there are any questions, you can, as I said before, either type your question in the chat or ask it directly.
Sir, can I ask one question?
Yes, go on. Can you sorry, I'm sorry.
Yes.
For all people who are asking questions, can you first introduce yourself by stating your name and affiliation so that the speaker knows who is he talking to, and then you ask your question. Thank you.
Yes, sir. My name is Hardik M. Pandya. I am from India.
Okay,
and
thank you.
I am an assistant professor in VVP Engineering College in electrical department.
Thank you.
Although my specialization is in means my area of interest at present, I am pursuing my PhD in power quality, but I am also interested into PV integration with association to power electronics.
That's
That is
fine.
one of the purpose to attend this workshop. So,
Yeah.
sir, my question is that you have introduced many of these new technologies related to the increase of cell efficiency by introducing some semiconductor physics. So, as far as sir, thermal conductivity is concerned, means cell temperature. So, how this junction temperature would be able to get maintained when they are subjected to direct sunlight?
Yeah, I mean, you asked a good question because I mean, thermal increase in temperature. I mean, it's unavoidable that if you put a solar cell outdoors, it's going to increase in temperature. So various people do temperature dependent VOC and JOC measurements to see at low temperatures what's the main recombination process, and at high temperatures how does the performance change. And that's important test that people do to work out what the main loss processes are. So that's a fundamental test. To do standard tests in the lab, one of the recommendation and requirements for certification is to maintain device temperature to room temperature, 25 degrees Celsius. But in terms of outdoor applications, you want to test the stability of your device. And one of the key thresholds that, one of the key things you have to do to convince an investor that your device can last outdoors is called the damp heat test, where you heat your device up to 85 degrees Celsius in an environment of 85% relative humidity, and test whether this can maintain its performance over 1,000 hours. So that's one of the standard tests that people do. So to answer your question, for standard testing, you would maintain the temperature by having a water-cooled stage. But for deployment of the technology, you need to test the ability of a device to withstand high temperatures.
Sir, one more question. Can I add it?
Yeah, go on.
Sir, there was one of the books that is written by Professor Chetan Singh Solankri from IIT Bombay related to solar PV, where he mentioned one of the technologies to increase the efficiency so that there is less reflection of the sun rays is surface coating, surface refractive coating. So is there any advancement in that technology? Means any new things have been developed or added, or still this thing is followed?
Yeah, I mean that actually is so. Okay, so what you're talking about is the anti-reflection coating. So that is currently used in commercial silicon solar cells. You would, for example, use silicon nitride for anti-reflection coatings. For new technologies, you have to think about what the stacks are, because the most effective anti-reflection coating depends on the refractive index of the various different layers that you're using. And of course, if you change material, you change the refractive index. So for example, for perovskite silicon tandems, for the perovskite top cell, you need to have a transparent conducting oxide. And what people have found to be quite effective as an anti-reflection coating there is lithium fluoride or magnesium fluoride. And people are doing optical simulations to work out the optimum thickness for these materials. But there are other groups, I mean, I don't do this myself, but there are other groups working on developing new anti-reflection coating materials.
Okay, thank you, sir.
Yeah.
Sir, I have a question. I am Dr. Sharmila from College of Engineering, Guindy, Anna University. I am working as associate professor in the department of EEE. So my question is, it was a nice presentation, Robert, sir. And the thing is, like you are telling for 40 years, you're going to work on a material. If it is so, what are the new materials you are trying to suggest, and how will you handle the disposal of these materials, which were already there in India for 25 years? And in continuation to it, the standard test condition says 1000 watts per meter squared at 25 degrees Celsius. But in Indian conditions, we never get this ambient condition of 25 degrees Celsius. So what do you recommend for India, this standard test condition? Is there any work going on to change the standard test conditions? Okay. Because I am teaching this solar photovoltaic, I have this doubt for quite a long time. Right. And what is the best viable technology for countries like India? Because our ambient temperature is totally different from your place.
I mean, you asked a good question. I mean, these standard tests were developed for the PV manufacturer, because I mean, in terms of the cost of production, PV manufacturer, they have to have one test that they do, which can satisfy the investor. So, the test I mentioned, 85 degrees C, 85% relative humidity. that is a standard test that's been developed. And where that came from is from outdoor testing that people have done on silicon PV. So these are accelerated degradation testing protocols for silicon PV, because nowadays people understand very quite well what the degradation pathways are and what the various ways in which you can stress a silicon device to test and predict whether it can last for 25 years. But I mean, of course, for India, I mean, it's more a question of what tests you would do for new materials, because these tests have been developed for silicon, but for new materials they have unknown degradation pathway. Because if you look at the perovskites, that has only been developed for 10 years, well, 10 to 12 years, and of course, it's not possible for people in that time to have a device outdoors and measure the performance over a 40-year period. That's too slow. So it's only beginning so what people making perovskites are doing right now is they're using the protocols that were developed for silicon technology, and that is simply for the purpose of satisfying investors. Whether the device can actually last for 25 years remains an open question, and it's something that will be that the field will be working on in the near future, as field data comes in, as people start collecting field data in various different parts of the world, including India, including Saudi Arabia, for example. As that data comes in, people can use that data to inform and develop new methods for accelerated degradation testing. And I would expect that these protocols will evolve over time as people have more data and more confidence over the reliability of that data. And one of the emerging areas is to use the new machine learning models to integrate this data and develop new accelerated testing protocols. So I mean, to answer your question, I mean, yes, these solar cells have to be deployed worldwide, but the fact is that when it comes to standards, there needs to be just one standard that a manufacturer tests their devices against.
Yeah, I have one question. Yeah,
Sure.
This is Shivaditya Chatterjee from. I am a design engineer currently working as an Arbutus consultant in India, Pune. So, sir, my question is that you said about the new photovoltaic materials that are coming up in near futures and as well. What about the status of the critical mineral resources? Like
Okay.
if we go for the energy map, we have to check and we have to balance up that equation also.
Yeah.
Because you cannot just go on and inventing stuff. So innovations will be there. So how you're balancing that, the critical mineral resources?
Sure. Yeah, I think your question actually relates to one of the questions from the previous speaker. Sorry, I didn't answer that. Yeah, so I mean that's definitely very important. And what's happening more now is people are doing more life cycle analyses to think about exactly as you asked, are we what is our usage of the Earth's resources? And one of the things that requirements was that people identified from the roadmap from last year was to change the materials which are used and to switch them towards materials which don't rely on scarce elements or expensive elements. Because I mean, when you develop a new technology for the first time, the main thing you're worried about is the efficiency, and you're putting together the various different layers and controlling the layers using the method that you best think will improve the efficiencies as much as possible. But once you reach a certain level, and silicon's already reached that, you then think about how you can improve this technology so that you have a reduced reliance on scarce resources. So in the case of silicon, people used to use silver metallization. That is now being replaced with copper, which is much more abundant and a lot cheaper. For the silicon heterojunction cell, people are using transparent conducting oxides based off indium tin oxide, and that is also used in perovskite silicon tandems, as well as many other thin film technologies. So of course, indium is a scarce element, and there's a lot of groups who are working on developing and designing new transparent conducting oxides, which are indium free and which are based off abundant elements. I mean, if we look at the perovskites themselves, I mean, perovskite is methammonium lead iodide, or people looking at alternatives to methammonium. But I mean, all the constituent elements are abundant in that. The main problem is that it's toxic. At the same time, there's a lot of work being done right now to address the toxicity issues associated with lead. For example, people are developing coatings that can go into solar cells, which can sequester lead before it leaches out into the soil. And people are also looking at what's being done with cadmium telluride, because First Solar, which is the main manufacturer for cadmium telluride solar cells worldwide, they have a very successful recycling program. So even though cadmium and tellurium are toxic, cadmium telluride itself is not toxic, and it's encapsulated within the glass encapsulation layers that comes with the solar cell. So First Solar, they have a scheme in which they sell to the customer the solar cell, and then at the end of life they would then take that back and then recycle it. And people are also thinking of, perovskite manufacturers are also thinking about that for their modules as they go into market. They're thinking about how we can develop a business model in which they can offer a recycling scheme as well for the perovskites. And there's some recent papers in Nature Sustainability which look into how you can close the device manufacturing cycle, where you can, because the peroxide absorber itself, it's water soluble, so you can take that and then dissolve it into a polar solvent and then extract the constituent elements out and then use those as precursors, so you can close the device life cycle. Of course, I mean, even though there's these technologies to address the issues, toxicity issues around lead, there's still questions about will people be willing to buy lead-based solar cells, and that's why people such as myself and as well as my colleagues are working on developing lead-free technologies which are can perform as well as the perovskites, but which don't have toxic elements. And especially we're working on absorbers based off, for example, bismuth, which is not toxic at all. That's bismuth is being used to replace lead in many applications. For example, in solder, people used to use lead tin solder. Now they're using bismuth tin solder. And the abundance of bismuth is sufficient for commercialization and is sufficient for terawatt scale deployment. Yeah, so to answer your question, I mean, there's a lot of thought that's going into how do we replace scarce elements being used in these devices, and how do we close the device lifecycle to have a circular economy. And I think probably the most important area right now is not really in terms of the absorbers themselves, but really in terms of the contact materials, the metal contacts and the transparent conducting oxides.
Yeah, that's a nice explanation from you. I just want to last add up on that complying to whatever you just said right now regarding the near future, whatever the changes will be coming up for the IEC and IEEE standards for this case, what you have just explained, because even in our condition, the whatever the panels are coming up, it's are complying to IEC standards or IEEE standards. So according to that, whether it will be changing or it will be modified in near futures, right?
Yeah, I mean, it probably will be modified in the near future. So, I mean, you mentioned the IEC standards. So the IEC standards include standards for stability testing. And, as I mentioned, those were developed for silicon PV. And right now, perovskite manufacturers are using the same standards. But I mean, one of the important areas in the field is to develop new protocols for new technologies, which have different degradation pathways to silicon. So, I mean, in the near future, I'm expecting probably in the next 5 years or so, you'll probably see new protocols being written for these emerging technologies. And one of the things that we identified in this roadmap was to have a central team in the UK that can do this accelerated degradation testing. For example, there's a team based in Loughborough in Crest which does device certification, but there also needs to be a team within the national facility in the UK to work on developing these new protocols for accelerated degradation testing, and which can work with teams in other places in the world to write these new protocols for the IEC.
Robert, I have one more question. Robert, one more question I have.
Yeah.
If you say that in India we use this cadmium telluride based cells most commonly for the polycrystalline seems to be affordable for most of the Indian applications, solar rooftop applications, etc. So after the lifetime of 25 years, how do you separate them? Because in India we don't have any particular plan now how to dispose these materials, because it is going to be highly a carcinogenic substance, cadmium telluride, as you rightly said.
Right.
How India will handle these substances? Whether this future perovskite photovoltaics can occupy the Indian condition requirements, because we are having an ambitious target of 175 gigawatts, out of which 100 gigawatts will be through solar only. So can you suggest what would be the?
Yeah. So I think that's a good question, and I don't think anyone has a good answer to that right now. This is something that people familiar with the Indian.
Hello, Robert. I'm sorry. This question will be answered later.
Okay.
As the one which is typed in the chat box, because we have to stick strictly to the schedule, because people may be joining individual talks.
Okay.
So the colleague who asked the question, can you please remember what you wanted to ask or type it in the chat box? I have another question in the chat box and I will ask it later on. I keep muting people who forget to do so, but there are a lot of you. Can you please mute your... Interesting, I can't mute all of them.
You should be able to mute them all.
No, I can't. This one in particular, I can't.
You put them in the waiting room. Punishment.
Okay, so I managed one. Anyway, I'm sorry about this technical glitch for a second, and I do apologize once again for interrupting answering the question, but we have to really stick to the schedule because people are joining individual talks. We are not in the same room. We are all around the world, so we have to be a bit strict about this. So our next talk is by Professor Matthew Halsall from the University of Manchester, and this will be on solar PV technology stability and efficiency, which I assume, because I'm not even close to be an expert in this area, I assume it will be related to what Robert was talking about, and probably two of them can manage to answer this question that we had to interrupt, if you like, at the moment. So
yeah, I think we'll. Whoops, sorry. We should actually. It's working quite well. I think a lot of what Robert said covers stuff that I hadn't got time to do. So it's
excellent. So Matthew, the floor is yours.
Okay. Okay. Is everyone seeing the correct screen? They're seeing the.
Yes.
Okay. Right. So I'm a professor in Tripoli, Manchester, a colleague of Jovica's. But I'm working in a very different area. So by background, I'm a semiconductor physicist, and our group has for 30 or 40 years worked on defects in semiconductors for all sorts of applications. So we've worked on LEDs and transistors, and one of our activities for the last 15 or so years has been defects in silicon PV. So the talk you're going to get now is very much the other side of aimed on traditional technologies. And so it's complementary. I think it's quite complementary to Robert. I mean, he introduced silicon, and so I'm going to talk about silicon, but I'm going to talk about a particular aspect of silicon, the role of defects and degradation. But he rather usefully introduced the design of silicon cells, which I didn't go into so much detail on, and also, of course, he covered technologies other than silicon, which I don't. Okay, so a little bit of again, usefully, Robert did talk about this in more detail, but I will just introduce where we are with conventional technologies. So the exponential growth in solar PV. So this is a log scale graph on the gigawatts generating capacity, installed capacity, and time, and you can see that there's obviously an enormous growth in installed capacity. Most of these, this is from the same report, actually, that one of the reports that Robert showed, the Fraunhofer report from 2018. So 2020, sorry, and but it shows the growth is enormous. And this is a nice little graph, which was taken from NREL, actually, from the National Renewable Energy Labs in Colorado. And this shows a kind of correlation or connection between the standard price of a module in dollars per watt and the shipment of modules. And again, this time both log scales, and there's some, okay, when you take log scales on both sides, you tend to get straight lines, but there seems to be some obvious correlation. The cheaper the module is, the more you sell, the more installed capacity you get. So the price of the cell is incredibly important. move. I think I'll check my timing, so I'll move that down and I can see where we are. Okay. Right. I'll come back to this one. All right. So, so this is, I think, the only slide which I have in common with Robert. This is from the Fraunhofer report in 2020, and this shows the installed capacity, the production of different kinds of cell year by year. And as Robert said, in the last year on this graph here, silicon totally dominates. More than 90% of sales were silicon solar cells. What Robert didn't concentrate on is also the increasing dominance of monocrystalline silicon. And in fact, I happen to know, I've heard the figure from last year, and monocrystalline silicon is now pushing very close to 80% of all sales of solar PV. And monocrystalline silicon is where the crystal of silicon is a single crystal of silicon. The alternative is multicrystalline silicon. I'm going to say a little bit about the manufacture to put some background into where we're coming from on this. But monocrystalline silicon, you basically grow a large crystal of silicon and you saw it up to make devices, the solar cells. Multicrystalline silicon, generally what's happened is you melt silicon, you pour it into an ingot and you slice it. Multi-silicon traditionally was cheap. You can tell the difference by looking at them. The multicrystalline silicon are the cells that have patination on them, the single crystal are smooth. The multicrystalline silicon were traditionally cheap but less efficient. But basically over time, as I'm going to say throughout this presentation, over time manufacturers have got to grips with how to mass produce silicon cheaply and easily, and in particular how to mass produce mono silicon, which is the more efficient variety. That's due to the presence of grain boundaries and therefore impurities in multicrystalline silicon. And I believe there's only 1 or 2 factories left in the world now making multicrystalline silicon. Nearly everybody's going over to mono silicon. Why are they doing that? Well, again, Robert touched on this, but it's all about efficiency. The monosilicon we see here in the orange curve has always been more efficient than the multicrystalline silicon, and the efficiencies have been getting better, and the cheapness of the monocrystalline silicon is approaching that of multicrystalline silicon. So people, manufacturers and people buying the modules prefer the higher efficiency cells, shorter payback time, and so the world's moving over to producing monocrystalline silicon, which is great for our group as it happens, because we find it much easier to work in monocrystalline silicon, the kind of things we do, than people who work on multicrystalline silicon. So that's good for us, but of course the reason it's been happening is because of the efficiency. Again, Robert mentioned we have this limit, the Shockley-Queisser limit, which is around about 29%. So this is a mass-produced average. The best solar cells you can commercially buy now, I think, some power are something like 23.5 or 24% efficient. They're expensive. The normal bulk standard stuff's 21%. So there's some way to go to achieve the Shockley-Queisser limit. You can't get absolutely at it. As again, Robert pointed out, different designs have different optimal efficiencies or perfect efficiencies, but we should be able to get to 27% before we start to hit this kind of limit using the kind of technologies we know of today. Actually, there are a few ways you might be able to improve that a bit further. Using plasmonics, for instance, you might be able to get to 30 or 31% theoretical. So silicon's got a way to go, and we're working on improving that in our own way. Okay, so this is a nice picture just to show where grid parity was in different years. Obviously less sunshine the further north you are, and it's increased to the point at which now grid parity is inside the UK. So we can generate power more cheaply than any other way inside the UK. The important information on this curve is down the bottom here. To achieve these kind of predictions, we have to assume 25 years of lifetime with some interest rate, with some maintenance costs. So what is really important, Robert had a slide that showed this, is the stability of the cell. And it goes a bit beyond simply the cost, apparent cost. It also goes to the confidence of the investor. The investor has to be confident that they're going to lend you that money and they'll get a return. They have to be confident that the cells are going to last 25 years. And so, whereas the accelerated tests, which Robert mentioned, are standard approved tests, there is still the element of, does the investor believe them or not? That's still built in there. Okay, and of course, it's making the national newspapers. This is the Manchester Guardian, 24th of April this year, had a very long article extolling solar energy and saying it's very cheap, insanely cheap is how they put it. But yes, I think it's the push of the article is true, is that everybody is, even people who are pro PV, advocates of PV, have been surprised by how cheap and how rapidly solar PV energy has become. Okay, so I'm going to talk about this from a materials perspective, and it's all going to be silicon. Okay, you're right. So I'm not going to talk about the developing technologies. I will admit to, before we get to any discussion about this afterwards, I will admit to being a new technology cynic. I have a vested interest, of course. We work on silicon, but I think that that there's a lot of problems to be resolved, and it's not clear they will be resolved. So I think that, you know, silicon's going to be around for a long time yet, and so it's important that we make it work as well as we can. So the things I'm going to talk about in my talk are going to be, what can we do about the cost? So I'm going to concentrate on silicon, the properties of silicon itself, how it's made for solar PV, and what we can as material scientists do to improve these things. So what can we do to improve the cost? What can we do to improve the efficiency? How can we improve the stability? And then this thing that occupied much of the conversation at the end of the last talk, sustainability. How can we make sure that we can produce enough of these solar cells that we can meet the demands of mankind for energy production in a way that doesn't deplete the planet of resources or is sustainable? Okay, so again, Robert showed this, but I'll show it again. I wasn't going to go into great detail. So how does a solar cell work? Well, simple physics is light comes in. You think of it as photons, packet of energy, that creates an electron and hole pair, as it's called in silicon. So it breaks a bond, it creates an electron. The broken bond that's left behind is thought of as a positively charged particle we call a hole. And then this thing is inside what's called a p-n junction, and the p-n junction naturally attracts electrons to one contact and holes to the other. So in the case of this is a PERC cell. In the case of the majority of cells now manufactured and sold are monocrystalline PERC cells. So what will happen is that the hole will find its way to the p-type material at the back contact, which is aluminium for contact, and the electron will find its way to the front contact, which is silver. And then we have some other complications. We have the already mentioned anti-reflection coating, which is usually silicon nitride. Silicon nitride performs two roles. One is that it's an anti-reflection coating, and it has the perfect refractive index for that, which for silicon is 2. And it also plays the role of, because of the way it's deposited from a plasma, it pushes hydrogen into the silicon, and hydrogen is usually a good thing to have incorporated in the silicon. As you'll see in one of my later slides, not universally, but silicon defects are generally passivated by hydrogen, we call turned off. So we can pushing hydrogen in from the front coating is a good thing, and generally. Okay, so there's a lot of stuff I teach in my undergraduate course. How do we make silicon? So the main detraction from solar silicon as a material. Okay, the main detraction from solar silicon as a
Someone is.
Adi?
Just a second. I'm trying to locate the.
Okay, so it's okay. We're okay. So the main detraction from silicon, at least philosophically, is it's a high energy, high temperature material. You have to smelt it with carbon in the same way as you do iron. That produces what's called metallurgical grade silicon. So first of all, you mine it somewhere. So that's straightforward. Silicon makes up 27% of the Earth's crust. There's plenty of it around. We can find it on the beach or the desert. We select a source of silicon which is low in impurities, because that helps from the beginning. We smelt it with carbon to produce lumps of what we call metallurgical grade silicon. That's a high energy process, obviously. And then we react it with chlorine to refine it further. That's called the Siemens process. That's also a high temperature and uses chlorine, which isn't a terribly nice compound or element. But at the end of the day, we end up with the thing shown at the top here, which we call feedstock, which is relatively pure silicon, which we can use to make our solar cells with. And then for monocrystalline silicon, what we do next is we melt it into a furnace, which is basically a silicon dioxide crucible. You melt you heat that up to some huge temperatures of 1400 degrees C or whatever to melt the silicon, and then you put a single crystal seed into here, and then you draw it out and rotate it. Oops, sorry. Draw it out and rotate it so that you get a large boule, single crystal of silicon, which is shown on the left in the ingot. That's then sliced up, and then you do lots of processes, diffusing in contacts, etc., and dopants to create a solar cell. And here we are. So that's actually out of date. It's less than that now, as I'm going to show you. The cost of the actual cell is quite low. So so what happens, relevant for my rest of my talk, what happens here? Oxygen gets incorporated because we have a silica crucible, silicon dioxide crucible. That is actually historically been viewed as a good thing, because oxygen performs the role that carbon does in steel. Oxygen hardens the silicon so it can be sawn into thin wafers. So that's good, but then we shall see later on that oxygen is bad in some ways. Okay, so cost. So this is from the Fraunhofer report. Different countries manufacture, but if you look at the cheapest one, which is China, you can see that the silicon itself, that's the darkish blue category, is actually a very small cost of this total cell now. The processing is a bit more, the metallization, but most of the cost is putting the thing into a module, putting an inverter on it, encapsulating it, and then this is the module cost. It doesn't incorporate things like getting a guy to climb a ladder and put it on the roof, for instance, which has some cost as well. So the actual manufacture of solar cells now, the material itself is not an issue. Okay, so they've got that off. The industry has solved those problems. So is the cost of the material any more a problem? Well, no. It's a tiny fraction of the module cost. So the actual industrial manufacture of silicon is not a limitation. Processing is more. It's a high melting point material that uses lots of energy, but the metallization is a sustainability issue. And so actually so is the silicon nitride, which I'll talk about as well, and I'll discuss that later. So no, as a person working in looking at defects in silicon, they more or less solve the problems of making silicon single crystalline and pure enough to work. Okay, so but when you've done all that, you smelt silicon from sand, you're always going to end up with a load of other stuff in there, always inevitably. Also, all of these transition metals over here, so you're going to end up with iron, lots of iron, scandium, cobalt, chromium, nickel, all these things will turn up at very low densities, parts per million. But in a silicon solar cell, the electrons and holes you generate have to wander through in atomic terms, a long way to get to their contacts. And if they encounter what we call a trap, which is a defect state that captures the electron, then the energy will be lost. So all these things, presence of all these things are undesirable. So one of the games that we've been playing for the last 10 or so years is looking at which metals and collaborating with manufacturers of silicon solar cells to look at which metals are particularly damaging. Every time you refine silicon, it takes energy, it costs money. So what the manufacturers would really like to know is that all the problems they're having with the lifetime is due to a particular element, because then they can change their process or indeed select the feedstock to avoid that particular element. Okay, so I've just said all that. If you create traps from impurities, that causes that captures electrons. This is called shock recombination, or SRH recombination. We looked at that for 15 odd years, and we use a technique called DLTS, deep level transient spectroscopy, which I'm going to show you some spectra. I'm not going to describe how it works, but basically it's a mechanism, it's a technique that observes the thermal emission of electrons from traps in solar silicon, and it gives you a kind of fingerprint of those defect levels, and we can relate that to the presence of particular elements, and also what the impact is on the lifetime of the carriers, which is what reduces the efficiency. Okay, so I've said that already. We can take out damaged elements. That takes energy. Okay, so so this is a particular piece of work we did about 3 years ago now. So this is in collaboration with Sun Edison. It's a company in Portland, Oregon, actually just been taken over by a Chinese company, but they're still making solar silicon. And they developed this technique called, which is one of the contributions to the cheapening of solar silicon, continuous Czochralski. What normally happens in Czochralski is you grow a single ingot, you take it out, you saw it up, you refeed, you fill it, you empty out the crucible, you refill it, you melt it again, and so on. And that's obviously a slow and more involved process. What they do in continuous Czochralski is they just keep on growing the ingot. They put it to a certain level, they saw it off, and then they carry on pulling. And this cheapens the process, makes it process. But it does mean that certain impurities tend to build up. The whole idea of Czochralski is the impurities stay in the molten silicon. That's why it works. That's why you get such pure silicon. But certain elements don't do that very well. And one of those is carbon. And so we have a high level of carbon in their material, higher level than is normal. 10, still parts per million, but higher than normal. Oxygen's in there anyway, because I've already said it comes in from the crucible, and in some ways it's desirable because it hardens the silicon for sawing. But then when you make the silicon cell, you push hydrogen in. And we found, and they came to us because they were having a problem in the lifetime of the minority carriers, which I'll come to in a moment, which was reducing the efficiency of the cells they made. And it turns out that there is a complex of oxygen, carbon, and hydrogen formed under certain conditions. This is actually, it's actually minority carrier transient spectroscopy, but it's a form of DLTS. We see an emission peak here at a particular temperature, and we have some friends over in the University of Aveiro in Portugal who do calculations, and they were able to identify this as a complex of carbon, oxygen, and hydrogen. What was the impact on the cell material? Well, how do we quantify the impact it has on the cell? Well, what people working in solar PV worry a lot about, or think a lot about, is what we call minority carrier lifetime. What this means is when a photon from the sun creates an electron, if it's in p-type silicon, which is what's used as the absorber for 95% of solar cells currently, that electron is a minority carrier. There's less of it around than there are holes. And we have to collect that at the contact. And if we don't collect it, that's a loss. And so what we can measure or define is something called a minority carrier lifetime. And that's how long the electron will exist in this p-type silicon before it recombines with a hole by either naturally through something like Auger or by the presence of a defect. And the way of measuring minority, we in our lab, we use a microwave process. So we have a mapper that illuminates with a pulse of light a region of the cell, and then a microwave pulse is sent in, it's reflected from the cell, and the reflectivity of the silicon depends on how many minority carriers there are there. So we get decay, and we can measure the lifetime of the minority carrier, and we can map that. So this is a 4 centimeter by 4 centimeter region of Sun Edison solar silicon, and the lifetime is here. And you can see that on the left-hand side here, it's mostly red. So the lifetime has shortened, and the average lifetime is less than it should be. And then after annealing at 200 degrees C, we predicted that we can destroy this complex by annealing at 200 degrees C. It's been destroyed. And so they changed their process to put in this extra step, which would ensure the destruction after the firing process. It's called this extra anneal. So they basically waited at 200 degrees C for a bit longer than they needed to. And that was effective at destroying this defect and restoring the long lifetimes. Okay, that was published in this paper here. Okay, so the other kind of things we used to look at are metals. And so some metals are really, really damaging. So this is vanadium, which is one of the transition metals, which is found in the Earth's crust, obviously, as I said. In this case, we deliberately introduced vanadium. So we took float zone silicon. Float zone silicon is ultra pure silicon. It has essentially no impurities in it by any measure, or almost none, very low impurities, and no oxygen either, actually, or very low oxygen. And then we introduced vanadium by implantation process, and we annealed it to reform the crystal, the silicon crystal. And then when we did that, we found in DLTS, again, these correspond to traps that are emitting electrons back into the conduction band, and we can see a series of peaks. And these are like fingerprints. We know that these correspond to particular energy levels. They're vanadium related. We deduce that because they've appeared when we put vanadium in. If we put other metals in, we don't see them. They also have some tendency to some dependence on depth. We can measure depth with DLTS for a few microns anyway. We can look at the depth away from the surface the concentration of this particular trap. So we do that in this case, and we find that the trap increases. So that suggests that hydrogen is passivating them. Okay, because we introduce hydrogen at the surface, most of them, but it doesn't seem to passivate number 4. So and this is a small amount of vanadium, and also the hydrogen isn't very effective compared to most metals. Iron is very effectively passivated by hydrogen. So our conclusion from this, and we published it about 3 years ago now, was that vanadium is a really damaging metal, and if you try and avoid that from your feedstock, you'll be better off. Okay, so after all that work, is the impact of impurities on efficiency still an issue? I think most people in the field would say no. I think they've been solved. The problems have been solved. We've been working it for 10 years with various manufacturers, and the number of times they've come to us to ask about probleming defects in their material has gone down. They seem to be happy that they've solved those problems now. And you can see, this is just taken from a website, Clean Energy Reviews. You can see that commercial cells are becoming really efficient. You know, again, they're getting up towards, you know, when solar cells were first manufactured, you were looking at 10% efficiencies 30 years ago, 40 years ago. Now we're up to the 20-something% efficiencies. And we know the fundamental limit for these designs of cells is at the order of 26% anyway. So really efficiencies are moving in the right direction, and they are no longer limited by impurities. People have solved those problems. So I've stuck this in. So, oops, backwards. I just lifted this as a recent example. So this is actually N-types. That's another variant which gets around the boron oxygen problem I'm about to talk about. But they're reporting in the lab 25%, and we expect, you know, what you see in the company's lab is going to be at the market in 10 years. So really, competing technologies have to bear in mind that they may be achieving these in the lab now, but so is silicon, and silicon will be there by the time anything else gets to the market. Okay, so that's impurity story. So degradation, and this is what we work on now, because there are basically two long-standing problems of silicon solar cells which relate to degradation, and they're too poorly understood. No, not two together. There are two poorly understood processes, and they impact strongly on cell efficiency over time. And these are referred to in the community as BOLID, which is boron oxygen-like induced degradation. And as it says, it's related to the presence of boron and oxygen, which I'll describe. And the other one is light and elevated temperature degradation, or induced degradation. I missed induced in that it's deleted. And this is an area which academic groups can still make an impact. Because they're long-standing and not solved. And they've been known about for decades, particularly in the case of BOLID. BOLID's been known about for 40 years, and it's been a real mystery. And I think it's not an exaggeration to say that it's one of the outstanding mysteries in solid-state physics. What is doing this? We don't know. We still, until very recently, had no idea really. And we had some behavioral information, so we knew how it behaved, but we didn't know what it was. And this is losing the equivalent of millions of tons of carbon annually with the adoption of silicon technology. So it's a really important defect to try and understand. And we're looking at both of these, LETID and BOLID, which I'm going to talk about one after the other. So when you make your solar cell, boron is used to make the P-type material, the absorber for the solar cell in the majority of modern solar cells. Oxygen is present because it's Krakowski silicon, and oxygen is present. And it's difficult to get away from that. People have been playing around trying to put nitrogen in instead to harden the silicon, but nitrogen also produces various defects which are a problem. So at the moment, we still have oxygen in there. It's been known for decades that if you have those two elements present, then when you turn on the light, you expose the cell, a freshly made cell, to sunlight. Within a few hours, its efficiency drops by typically something like 5 to 10% relative. So a cell that might be 23% will go down to 21% after it's been exposed to sunlight for a few hours. And as I say, it's been known about for 40 years, and there's lots of behavioral information, which you can see here. This is a result from Brett Hallam. So I haven't given it an assignation, but it's Brett Hallam in University of New South Wales. And he's looking at in this case, he's represented it by the open circuit voltage, and the open circuit voltage goes down as we go through the cell, and that is an indication of degradation. And there's even neater show here. If you do it in a log scale here, you can see that it seems to have two rates, and that's well established. There seem to be two defects at least involved, two forms, two states. We think probably three states to the defect. So it's a defect that's changing its state, probably negative U as we call it in defect science. The other interesting thing is here is that they did comparison with gallium. Gallium does not degrade, or maybe it does. So this is something else we're looking at, and manufacturers are going over to gallium because it gets around this problem. But gallium has its own problems. Gallium does not diffuse well in silicon, so it's more difficult to get uniformity of doping, and those problems are being looked at and they're being overcome. But it's not simply a case of replacing gallium. The other prospective dopant is indium, but indium also has its own problems. Indium's quite interesting because it's controversial whether it degrades or not. We don't think it does, and some people do think it does. That's a different story. But indium's also a very scarce element, as we mentioned, so we best avoid it. Okay, so as I said before, the energy loss is around about 2% absolute or 10% relative, and essentially every current commercial silicon cell has some degree of degradation due to this bolide process. It shows rather complex behavior with illumination and annealing. What is agreed on, mounted of evidence and work by people over many years, is that it shows a linear dependence on the boron concentration and a quadratic on the oxygen concentration. So that suggests it's a compound of boron and two oxygens. This is Brett Hallam's work, more recent work, looking closely at it at the states. And it looks as though there are three states, and you can move between them by various annealing processes. So annealing at 200 destroys the recombination active. We know that, but it doesn't destroy it, it resets it, and then it reforms again when you illuminate, so you don't get around it that way. Hydrogenation does kill it, but it seems to be quite unstable. Hydrogen doesn't bind very well. So there's quite a lot known behaviorally about it, but not what it actually is. Okay, so this was our contribution to this in 2019. We found a defect in DLTS, and it turns out that you need quite a high temperature to ionize it, and that's not so much because it's high binding energy, because there's what's called a high activation energy. And so we found it, but it's curious because it's a donor, and it's a deep donor, and we don't understand how that causes the behavior. It shouldn't be. It should be a minority. It doesn't have the right characteristics, so that's a low cross section for. But what we find is that why do we find this? Nobody else has. The answer is it's a high temperature, and it's unusual. And we think no one's looked. That's all. It's as simple as that. We just think that nobody's looked for it before, at the right temperature range and the right pulse range. DLTS is pretty much the standard way to look for traps, and so it would have been looked at many times. But indeed, it has been looked at by us many times to try and find it. But probably people just didn't go to a high enough temperature. Simple as that. So we found this defect, but it has some strange behavior. It doesn't correlate with the degradation, it anti-correlates. So when we illuminate the sample, so going this way is illumination time, we find that this defect disappears and the degradation, it's the induced concentration. So this is essentially a normalized density of defect states, of degrading states. We can measure that. It's extracted from minority carrier lifetime. So basically, we've extracted this from minority carrier lifetime, and we find that as the degradation occurs, this defect disappears. And the same on a shorter scale here. You can see that we see it expanded this scale out. You see an almost perfect anti-correlation. So what we think is happening is that the state we see, which occurs in the as manufactured silicon, is a precursor to the state that does the degradation. And then we turn to theory. So we turn to our friends in Portugal, and they found a stable defect that would behave like this. And it has actually got 4 states, 2 of which are degenerate, so we don't see a difference between them. And one state is indeed a deep donor, which is the one we see, and that this when the Fermi level changes, when you illuminate it, this will convert to a damaging state, which is one of these states. And that's actually a shallow acceptor. So this is really interesting. So we kind of solved one problem, we found another one. Is that the next question is, why does this relatively shallow acceptor degrade the performance of the cell? And the answer at the moment, we're not sure, we don't know. But the evidence is very strong. We always see degradation. Whenever we see this, the precursor defect, and we expose it to light, we get degradation that anti-correlates to it. And so this was published in 2019. It's had 20,000 downloads. We've got 12 items in popular press, so national newspapers, Japan Times, etc. And actually the student was involved, Michelle Vaquero. Here's a Mexican student. She won the Research of the Year prize at Manchester University for finding this defect. Okay, so how do we solve it? We can find it's important. We can see something. We can measure it. We know it's there now. So that's an important discovery. What happens with gallium and indium? I've already said there are some problems with gallium and indium. They don't diffuse well in silicon. It's a different issue. But do we see the same sensors? Yes, we do. So this is that high temperature peak for boron, aluminium, indium, and gallium. Aluminium is a dopant, but it's not practical for other reasons. But so we see it for all those elements. But the behavior. So this is a capture cross section. The capture cross section changes. So that some way. So we think that they're structurally similar. We think that these metals from this group of the periodic table form a complex with 2 oxygen atoms commonly, but they are not electrically identical in their behavior. And for some reason, the boron degrades the activity of the cell. So that's ongoing research. We're still looking into that. Leated. So this is an even more intriguing effect. Again, more or less all current cells, even multicrystalline cells actually in silicon, show this degradation to some effect. It shows complex behavior. It's difficult to understand at the moment. The only thing that the many people working in the field agree on is some hydrogen is involved in this somewhere. And this is through some rather clever experiments that introduce hydrogen and deuterium, alternative hydrogens, and looking at the behavior of under degradation. And so we're pretty sure hydrogen's involved, but we don't know exactly how. What happens is even more strange, is we get a reduction in efficiency out of exposure to light. The rate of reduction depends on temperature, right? That's hence the thermally active degradation, induced degradation. Sorry, this is the type hastily it should be induced, and then it rebounds afterwards. So you end up with a cell which is as efficient after it's gone through this process. But the rate this happens depends on temperatures, and so one of the strange aspects of this is that if you put a cell on a roof in Cyprus, right, and it's really hot, the whole process cycle goes through, and it goes through the whole cycle going down, be degraded and rebounding, perhaps in a year, which over a 25-year life cycle of a cell isn't so much of a problem. However, if you put it in a roof in Germany, where it's cooler and the illumination is less, the process depends on illumination strongly as well, then the degradation can take 20 years to occur and recover. So over the lifetime of the cell, we lose a lot of power. That's 20% of the power, so a lot. So here's me just showing, this is also University of New South Wales, as Liv, one of our collaborators' data. And you see a degradation. So these are under open circuit and short circuit conditions. And you can see that 95 degrees C, so very high temperature, well, for terrestrial standards, the whole process is over and done with in 600 hours. Whereas at 50 degrees C, which is a more temperate climate, perhaps, it's slower. And so after 1400 hours, it's still degraded. And this takes the similar amount of time to recover. So very long periods, years, potentially. So yeah, so that's the process. We don't understand it. So we just been awarded this grant. We had it a year. Of course, it's been affected by COVID, which is very annoying. But we're looking at it, and we think we found a new complex, a boron hydrogen complex that no one's seen before. And we think this might be causing the problem. So here it is. This is breaking news. We're looking at this defect at the moment. It's one of our candidates for causing the problems. And this complex is its formation and dissociation is very complicated. We've already seen that from the DLTS data we have. So we looking into it to see if it could be correlating with leated and whether it's responsible. Basically, it's a donor. So what happens is you create a deep donor, which is damaging to the minority carrier lifetime under certain circumstances. Okay, sustainability. So quickly, so this is talked about a lot. So silver contacts, already 10% of the world's silver production is used for PV contacts. So it's a real problem. If we want to, we're going to we have exponential growth of PV installations, and so it's going to run. It's going to run into this problem, at some point in the next few years. The other one is not so much a sustainability, but undesirability. We use silane to create the anti-reflection layer and hydrogen reservoir. This is deposited from plasma. Silane is toxic, it's explosive, There have been many fatal accidents over the last I should say few decades. In fact, there was an explosion in Tokyo University a few years, I think about 20 years ago now, which killed some academics. It's terrible. So so people don't like it for obvious reasons. So you know, if we can replace those two things, that's something we can do for silicon. So of course, we're Manchester. Our solution is graphene, as always. So we've been looking at graphene oxide. So this is something else that Michelle did. So we spin graphene. Graphene oxide is like it's spun from solution. It's basically a layer of carbon and oxygen on the outside. The outside is negatively charged. It repels electrons. So it's good for keeping electrons away from the surface of silicon, where surface recombination occurs. And it also has the right refractive index. It has refractive index of 2, and you can just spin it on. You don't need to deposit it from high temperatures from a plasma or using silane or anything. So we can put that on and passivate the surface. So this is passivation. You can see not quite as good as silane, but not bad. And then the other thing we're doing is we're looking into graphene itself to replace silicon. Graphene is carbon, it's earth abundant. It's a good conductor. So and it can be screen printed, which silver is. So we're looking at that's actually the subject of our next grant proposal. But we're looking at replacing silver with graphene. Okay, so conclusions of our take on this is that silicon dominates the solar PV materials, and it's like to do so for some time yet. Well, you know, obviously other technologies are exciting and they've got great promise, but I think, you know, the investment in silicon is so great that it's going to be around for a decade or two, whatever happens really. The efficiencies are heading towards physical limits, and the material costs are low. So that's not so much a problem anymore. You know, there's not much mileage for researchers to work in that field, if you look at it that way. But there are degradation mechanisms, and this reduce the long time return from silicon cells, and we're looking at those, both of them. I'm an optimist about this. I think we can mass produce 26-27% efficient silicon solar cells in the next decade or two, and they'll be stable. And so I think that's the competition for other technologies. That's it, basically. Thank you. Oh, sorry, some acknowledgements. So acknowledgements, my co-workers, Tony Pico, Emeritus Professor, worked in this many years. Vladimir Markovich, who works on the Research Fellow. Ian Croman, a member of staff. Simon Hammersby and Ian Hawkins are experimental officers. Students, Jack Mullins, Michelle, Cheyenne, and Joyce. Theory, done at the University of Aveiro by Jose Coutinho and his company. And we get materials from Minsk. We get materials from Edison in Portland, and we get materials from the University of New South Wales. And actually, Michelle is now Research Fellow at the University of New South Wales, so she's moved out there. Okay, thank you.
Thank you, Matthew. Thanks very much. Again, fantastic talk and even better timekeeping. So we have, again, time for questions. So again, as before, could all people who are asking questions first introduce themselves by saying name and affiliation only, no need for a short CV, and then ask the question. And please, if you can, ask no more than 2 questions so that we can finish timely and give many people opportunity to ask questions. So any questions, please go ahead.
I've done them all.
So everything was very, very clear, or people went for lunch.
Maybe I says I'm standing between you and lunch. That's probably the problem.
Yeah, you were. Let me see what is it, chat box.
I noticed that this is focused on the Mediterranean. The group. I mean, you know, it's quite interesting that LETID has different degradation mechanisms. Actually, are quite dependent on conditions and insulation. So different problems in different places.
Any interest to ask further clarifications or questions from Professor Halsall? Well,
Well, everyone's stunned.
must have run for lunch.
We have one question in the
Go on,
chat.
go ahead.
We have a question in the chat.
Amorphous silicon, yeah. Well, amorphous silicon's kind of dropped off. Well, it's used, as Robert said actually in his talk. There is interest in amorphous silicon as a cladding material for silicon. You can improve the efficiency slightly. So there is, so that's where it may make a comeback. But the cells themselves, it's kind of gone off. Not so interesting. They're not very stable, and they're also it's a quite unpleasant process to make them. Again, it's lots of silane again. So people and basically it's the same story. So people who make bulk silicon, crystalline, monocrystalline silicon have just got their act together and make it very cheaply, and the other technologies don't compete. Yeah.
This is Shivaditya from Arbutus Consultant. I'm currently working as a design engineer.
Yeah.
So my question is that what are the new technologies that are coming up with the solar wafer cutting technology? So there are new things coming up in dimensionally. They are also getting smaller as well as bigger with the module size that are going up like 600 watt peak modules also.
Yeah.
So what are thought? Yes. Yeah. Go on.
So one of the growth areas in silicon is making bigger and bigger ingots. Growing ingots which are 12-inch, then 18-inch, and I think they're even aiming for even bigger. So making single mass production basically. So sawing technology has to keep up with that. I mean, there is an optimal thickness for the absorber in silicon, which is around 100 microns, which is pretty thin, but that's what they're at. So really the only issue with sawing is sawing larger ingots, A, and B, not wasting material. You obviously, when you saw, you remove some silicon, and so if you can, the thinner the wire is you use, the better. So that's the kind of growth areas in silicon processing. But again, the problems are being solved. It's amazing how the industry's moved on.
Anybody else? If not, thank you, Matthew, once again.
Welcome.
Hello?
Hello. Yep. You are. Oops.
There's nobody else. Okay, so thank you once again for a very good talk. And thank you all who have been here this morning. We are going to adjourn for lunch now and reconvene at 1 o'clock UK time or 2 o'clock Central European time with a series of talks on application of PV solar generation into power systems, which is the other aspect. We heard from Robert and Matthew about the materials used to produce these devices, and now we're going to hear from Alessandra, Chiara, and Berklin about how these devices are, or materials are used to produce photovoltaic panels, and how we try to implement and control them in electrical power systems with probably more focus towards the end of the afternoon on microgrids. So thank you once again for being here with us. Enjoy your lunch, and I'm looking forward to see you all at in about 70 minutes time. Thank you very much. The link will stay open, but if you are connected, please mute yourself. Thank you once again, Matthew and Robert.
Thank you very much. Thank you, guys.